Good morning, good afternoon, good evening, everybody, and welcome to Understanding DMVPN. My name is Brian McGahan. I am a CCIE in Routing and Switching Security Service Provider Data Center and a CCDE in Design. So for any questions that you guys have after the seminar, you can feel free to email me, bmcgahan@INE.com. Follow me on Twitter @BrianMcGahan or on linkedin.com/in/bmcgahan. Now, the format of today, we have a brief slide deck that I'm going to go through that talks about just some background information on DMVPN. But most of the time, we're going to be spending this live on the command line building the DMVPN and then talking about the overall design of it, talking about some of the more advanced issues that you could run into when we're talking about DMVPN. So first off, we're going to talk about what is DMVPN, why would you want to use it, and then we'll look at how DMVPN works on the command line. So what is DMVPN? It's a point-to-multipoint layer 3 overlay VPN. So it uses a logical hub and spoke topology, and direct spoke-to-spoke traffic is supported. The idea being that we have any-to-any communication over an encrypted media. So DMVPN is going to be using a combination of multi-point GRE tunnels or MGRE tunnels, the next top resolution protocol or NHRP, and then IPsec crypto profiles for encryption, and then a routing protocol of our choice, whether this be eigrp, OSPF, BGP, whatever, that we're going to be using for routing the traffic over the DMVPN tunnel. Okay, why would you want to use DMVPN? One of the main reasons is that it's independent of the SP access method. So the only requirement that we have is that we have IP connectivity between the sites. So we don't need to be on the same MPLS network. We don't need to be on the same provider. As long as you can ping between the sites, that's really the only requirement that we have for the DMVPN. Okay, the other big advantage is that the routing policy is not dictated by the service provider. So for example, if you're using an MPLS layer 3 VPN, it's usually going to be up to the provider what type of routing protocol design that you can use, whether you can use OSPF or eigrp or BGP for the routing protocol. But since this is an overlay VPN, it's going to be independent of the SP access method, and we can choose whatever routing design that we want. Okay, it's also highly scalable if properly designed. We're going to talk about some design issues in terms of single hubs and dual hubs, and talk about some of the scaling issues that you could potentially run into with the DMVPN. Okay, now how DMVPN works, it allows a full mesh of on-demand IPsec tunnels with a minimal configuration with using multi-point GRE, the next top resolution protocol, IPsec crypto profiles, and then routing. Okay, so it's going to reduce the need for a full mesh of static tunnel configurations, which we run into our full mesh problem, the n times n-1/2, where from a configuration point of view, we're going to only be using one logical MGRE tunnel interface for all of the connections, and then the tunnels are going to be created on demand between the nodes. Okay, technically, encryption is going to be optional, but 99% of the time, you would want to run encryption on top of the DMVPN. So from our examples, we're first going to look at DMVPN without encryption so we can do some packet captures and look at what's going on behind the scenes. Then we're going to talk about adding IPsec on top of this, and we'll see what are the changes when we're running IPsec in conjunction with the DMVPN. Okay, now DMVPN is going to create an on-demand tunnel between the nodes, where initially we're always going to have tunnels that go from the spokes to the hub. But the traffic patterns are going to trigger spoke-to-spoke tunnels depending on our routing protocol and depending on the traffic patterns. So this is going to solve the management scalability problem of configuring multiple tunnels between the sites. Like I mentioned, we're only going to need one logical GRE tunnel interface from a configuration point of view, and then this is going to allow us to do any-to-any communication over the network. Okay, so we're going to maintain tunnels based on traffic patterns, which means that the spoke-to-spoke tunnels are going to be on demand. And eventually those are going to time out based on the tunnel lifetime if we don't have traffic that's going between the spoke-to-spoke tunnels. Okay, now in order to implement DMVPN, we require two IGPs, both an underlay and an overlay. So both IP version 4 and IPv6 is supported for both the passenger protocol and the transport protocol. So we could run IPv4 DMVPN, we could run IPv6 DMVPN, or we could run a combination of both of them at the same time. Okay, now how DMVPN works from the hub to the spokes, we have two main components. The DMVPN hub, which is going to be the next hop resolution protocol server, or what we call the NHS, and the DMVPN spokes, which are going to be the next hop resolution clients, or the NHCs. So the idea is that the spokes or the clients are going to register with the hub, and the spokes are going to do this by manually specifying the hub's address. So we'll see this when we look at the configuration. We're always going to have a static mapping from the spokes to the hub, but the hub is going to be dynamically learning the spokes through this NHRP registration request. Okay, the hub is then going to dynamically learn both the spoke's VPN address and what we call the NBMA address, which is the overlay address and the underlay address. So the overlay address is what we're going to be running inside the tunnel or the VPN. And then the NBMA is going to be the underlay interface, the underlay addressing that we're using to establish the multi-point GRE tunnel. Okay, the spokes are going to establish the tunnels to the hub, and we're going to exchange IGP routing information over the tunnel. In our examples today, we're going to be using eigrp as our routing protocol of choice. Okay, now for the spoke-to-spoke tunnels, the idea is that we're going to be learning IGP routes about them. Spoke 1 is going to know spoke 2's routes via IGP learned from the tunnel interface to the hub. And the next hop is going to be spoke 2's VPN IP address for DMVPN phase 2. The next hop is going to be the hub's VPN address for DMVPN phase 3. And we're going to talk about on the command line the difference between DMVPN phase 2 and phase 3. So spoke 1 is going to ask for the resolution via the next hop server. It's going to ask for the real address or the underlay address of spoke 2. And it's going to be sent with an NHRP resolution request to the hub. And then the spoke-to-spoke tunnel is going to be formed. So the idea is that the hub is not going to be used in the data plane for the actual packet flow. The hub is only going to be used for the control plane information for the NHRP and for the initial flow of packets while we're in the middle of establishing the spoke-to-spoke tunnel. But 99% of the traffic spoke-to-spoke is going to go directly spoke-to-spoke as opposed to going up to the hub and then back down. Okay, some important messages that we need to talk about. We have the NHRP registration request. This is going to be where the spokes are registering their non-broadcast multi-access or their NBMA address and the VPN address to the next hop server. This is going to be required to build the spoke-to-spoke tunnels. Okay, we then have the resolution request. This is going to be the spokes talking to each other. So the spoke is going to query the hub for the NBMA to the VPN mapping for the other spoke, and it's going to be required to build the spoke-to-spoke tunnels. Okay, last but not least, we have the NHRP redirect message, where the next hop server is going to answer for spoke-to-spoke traffic flow. And as the data plane traffic goes from spoke to hub, we're going to redirect this back out the same interface, back out the same tunnel interface. And this is going to be used for DMVPN phase 3. Okay, so let's go ahead and take a look at the topology we're going to be using for today. We have router 5 is going to be our DMVPN hub, and router 1, 2, and 3. Router 1, 2, and 3 are going to be our DMVPN spokes. And then assuming we have time, we're going to look at using router 4 as a backup hub. Okay, so we're not going to be building this from scratch. We're going to be looking at an example from the documentation. And we're going to change this around for our particular usage. So we're going to start at the main documentation page. We're going to go down to networking software. So iOS and NXOS. We're going to go down to our release 15.3 M&T. Then we're going to go down to configuration guides. And we're going to go down to security. And then DMVPN is going to be documented under secure connectivity. Okay, we have Dynamic Multipoint VPN configuration guide. Okay, 99% of the stuff that we need to know is going to be under the first document here, Dynamic Multipoint VPN. And we're going to look at just their examples. So we have an example hub configuration and then the example spoke configuration. Okay, it says the following example, which requires the hub router for multipoint GRE and IPsec integration. No explicit configuration lines are needed for each spoke. That is, the hub is configured with global IPsec policy template that all spoke routers can talk to. In this example, eigrp is configured to run over the private physical interface and the tunnel interface. Okay, so we're going to copy this example out, and then I'm going to go line by line through this, and we're going to talk about what specifically they're doing in the configuration. So this is going to be our hub configuration. And then we also have the spoke configuration. Okay, it says in the following example, all spokes are configured the same except for the tunnel interface and the local interface address, thereby reducing necessary configurations for the users. So we're going to see that the configuration for DMVPN is very template based, where the only real change that we need on the DMVPN spokes is that they need a unique IP address configured on the tunnel interface itself. Okay, so under the DMVPN hub, we start with the crypto configuration, which we're going to hold off on for now, and we're going to come back to in a little bit. So we have the ISACAMP policy, which is the phase 1 negotiation. We have the pre-shared key, which is using a wildcard. So this means that we can authenticate any remote box using a single password. And then we have the crypto transform set, which is going to control how we're actually encrypting the traffic over the tunnel. In this case, they're using ESP with AES encryption and ESP with SHA-HMAC for the authenticator. Okay, another key important point here is that we're running mode transport instead of mode tunnel for the IPsec profile. And the reason why is that we already have GRE encapsulation on the tunnel, so we don't need to add a third IP header on the tunnel interface by adding the ESP IP header. Okay, so next we have the tunnel interface. The bandwidth is going to be related to the eigrp metric, so this is not going to be required. Okay, next it says for the IP MTU, ensure longer packets are fragmented before they're encrypted. Otherwise, the receiving router would have to do the reassembly. Okay, so this we do want. We don't want to have the DMVPN spokes have to do the reassembly. We would want the end host to have to do the reassembly. The following line must match on all nodes that want to use this MGRE tunnel, which is the IP NHRP authentication. Okay, so the authentication string needs to match on the hub and the spokes. Note that this line is required only on the hub, IP NHRP map multicast dynamic. So this is going to be for our routing protocols like eigrp, where we're using a multicast hello message in order to discover the neighbors, and then we're using unicast in order to synchronize the topology. But what this statement means is that when the spokes register to the hub, we're going to have a dynamic mapping for multicast that we can go ahead and form an IGP relationship from the hub down to the spokes. Okay, next, the following line must match on all nodes that want to use this MGRE tunnel. So we have the IP NHRP network ID, just a number that needs to match in order to form the tunnel interface. Okay, the NHRP hold time is not going to be required to be modified. We can leave that as the default. Okay, next it says turns off split horizon on the MGRE tunnel interface. Otherwise, eigrp will not advertise routes that are learned via the MGRE interface back out that interface. So eigrp, as we know, is a distance vector protocol. So when it receives an update in an interface, it's not going to turn around and send us the same update back out that same interface. But in this particular case, since we have the spoke advertising a route to the hub, and then the hub advertising the route back out the same interface, we do need to disable split horizon on the hub. Okay, so we're going to be using eigrp process number 1 in this example. Okay, next we're going to enable dynamic direct spoke-to-spoke tunnels when using eigrp. This is going to be a function of DMVPN phase 2, the no IP next hop self eigrp1 command. So we'll talk about this in more detail when we get to the command line. Okay, we have the IP TCP adjust MSS 1360. This relates to the IP MTU, that the IP header is 20 bytes, the TCP header is 20 bytes. So we take those 40 bytes, we subtract them from the IP MTU, and this is going to be the maximum segment size that we can use for the TCP communication. So the idea is that we're trying to get the end host to do fragmentation as opposed to the router to doing fragmentation. because it's going to be processor intensive and it's going to slow down the throughput of the tunnel if the router is the one doing the fragmentation and the reassembly. Okay, the delay is going to be a function of eigrp, so this is not going to be required. Okay, next we set the IPsec peer address to the Ethernet public interface. So this is the source of the tunnel. Okay, in our particular case, the source of the tunnel is going to be gigabit 0/1.100. So this is going to be our first change, that the tunnel source is gig 0/1.100. And the tunnel mode is GRE multipoint. So under a normal GRE tunnel, you would have the tunnel source and the tunnel destination. But in this case, we don't yet know the tunnel destinations until the DMVPN spokes register with the hub. Okay, so that's one of the key point differences between the single point-to-point GRE tunnel and the multi-point GRE tunnel, is that we don't specify the tunnel destination. Okay, next, the following line must match on all nodes that want to use this MGRE tunnel. So we have the tunnel key. And this is going to be exchanged in the data plane in the GRE header, so we need to make sure to match the tunnel key. Okay, then we have the IPsec profile being applied to the tunnel interface, the tunnel protection IPsec profile VPN profile. So this one we're going to hold off on until we get the basic tunnel up. We're going to look at some packet captures, talk about behind the scenes, what are the messages that are being used for the DMVPN, and then we'll come back and look at this with IPsec on top of it. Okay, we then have the interfaces that are sourcing the tunnel. Okay, in our particular case, we're going to be advertising the tunnel interface, which is going to be 155.1.0.0. So 155.100.0.0.255.255. And we're going to advertise our loopback network space, which is 150.1.0.0, 0.0.255.255, okay, into the eigrp process. Okay, additionally, the IP address on the tunnel is going to be 155.1.0.5 for router 5. And this is going to be the extent of what we need for the tunnel interface, okay, for the tunnel interface without using IPsec. Okay, so let's go ahead and apply this on router 5, which is going to be our DMVPN hub. And then our main verification here is going to be simply show DMVPN. Okay, under show DMVPN, we're going to be looking for dynamic registrations that come from the DMVPN spokes. And then we should see a list of the mappings between the NBMA addresses and the VPN addresses, which are the underlay, or the the underlay and the overlay addresses respectively. Okay, now before we configure the DMVPN spokes, we're going to go ahead and do a packet capture. So in this case, I'm running viral on the back end. So we're going to go to router 5's interface gig 0/1, and we're going to do a traffic capture. Okay, I'm going to leave everything as the default options. Let's go ahead and create the traffic capture. And let's now look at the configuration of the DMVPN spokes. Okay, so for the spoke configuration, we have the identical crypto ISACAMP policy. We have the identical transform set, and we have the identical crypto profile. So these attributes need to match between the hub and the spokes in order to form the IPsec tunnels. This is independent of the DMVPN itself. This is a function of IPsec. It's not a function of NHRP. Okay, so on the tunnel interface itself, we technically don't need the bandwidth. We're going to start on router 1, so our address is 155.1.0.1/24. Okay, the following line must match, which is the NHRP authentication. We then have the definition of the NHRP server, which is the hub, okay, which is permanently mapped to the static public address of the hub. So in our particular case here, we're going to be mapping 155.1.0.5 to its underlay address, which is 169.254.100.5. Okay, so we'll look at on the command line, when we use the question mark here, it specifies the second address is the NBMA address. So from a config point of view, this is one of those common problem areas that if you get these addresses backwards, then the tunnel is not going to come up. But we specified the VPN address first, which is the inner address on the hub. and then we specify its outer address, which is the non-broadcast multi-access address. Okay, we then have the mapping for multicast. This is going to be when we're sending our routing protocol hellos. We need to know in the GRE tunnel where we're going to replicate these to. So this is going to go to the NBMA address of the hub, so 169.254.100.5. Okay, the following line must match on all nodes that want to use this MGRE tunnel. So we have the NHRP network ID number 99, so matched on the hub. We have the NHRP hold time, not 100% required. Configures the hub router as the NHRP next hop server. So this is going to be the VPN address, which in our case is 155.1.0.5. So this is going to be where we're sending our NHRP resolution requests to. Okay, the delay is not going to be required. That's a function of eigrp. The tunnel source, as I mentioned, is going to be gig 0/1.100. Okay, so all the routers are on the shared segment for the underlay. Tunnel mode is GRE multipoint, which is the replacement for the tunnel destination. So the tunnel destination in this case is going to be the mapping between the VPN address and the NBMA address for the next hop server. Okay, then we have the tunnel key, which needs to match. And then the tunnel protection, which is going to be the IPsec configuration. We're going to come back to this in a little bit. Okay, so we have the eigrp process. On eigrp, we're going to be advertising 155.1.0.0, 0.0.255.255, and our loopback space, which is 150.1.0.0, 0.0.255.255. Okay, so let's go ahead and apply this on our first spoke, which is router 1. And we should get a message that we have an eigrp adjacency up to the DMVPN hub. Okay, some of the verifications we're going to look at are going to be the show IP NHRP. This shows the mapping saying that if we want to get to the VPN address 155.1.0.5, we need to send packets to 169.254.100.5. So if we do a ping to 155.1.0.5, this is going over the multi-point GRE tunnel from the spoke to the hub. Okay, so let's go ahead and look at our packet capture. And first, we're going to look for NHRP. Okay, we see the NHRP registration request that's coming from 169.254.100.1 going to 169.254.100.5. Okay, so inside NHRP, inside this mandatory part, we have a mapping between the source NBMA address and the source protocol address, or the VPN address. So we're basically telling the next hop server that if anybody wants to reach the address 155.1.0.1, they really need to send packets to 169.254.100.1. Okay, we then get the NHRP registration reply back from the hub. This is the acknowledgement saying, yes, you have registered successfully with the hub. Okay, if we then look at the pings, so let's look for ICMP, we're going to see two different IP headers. We have the inner header, which is going from 1 to 5, so 155.1.0.1 going to 155.1.0.5. And then the outer multi-point GRE header that's going from 169.254.100.1 to 169.254.100.5. So we have the VPN address, the 155s, and then we have the underlay address, which is the 169 address. Okay, likewise on the way back, we have the inner address, router 5, replying back to router 1. And then the VPN address on, or excuse me, the NBMA address on the outside, the 169.254.100.5, going to 169.254.100.1. Okay, so next let's go ahead and add another DMVPN spoke. Let's go ahead and add router 2. So the only change that we need to make is just the IP address on the interface. Okay, we should get a message that we have a routing protocol adjacency with the DMVPN hub. So if we look at the show IP eigrp neighbors, we have an adjacency to the inner address of the VPN, the 155.1.0.5. Okay, lastly, we have our third spoke, which is router 3, 155.1.0.3. And we have the adjacency up to the tunnel 155.1.0.5. Now, one thing that I did forget to do before we started here, there's some other interfaces that need to be disabled. So on router 3, I'm going to shut down interface gig 0/1.13 and gig 0/1.23. Okay, that go between the DMVPN spokes. Then on router 1, I'm going to shut down gig 0/1.146. And on router 4, we're going to shut down the interface that goes between router 4 and router 5. Okay, so gig 0/1.45 is going to be shut down, and then gig 0/1.146 likewise is going to be shut down. So basically, I'm just isolating the DMVPN network so that only eigrp is only running on the DMVPN interface. Okay, so from the DMVPN hub, we now look at the show DMVPN, and we see the mapping between the NBMA address, the 169.254.100.1, mapping to 155.1.0.1. Okay, likewise, we see router 2 and router 3 registered. So this now means that anytime we want to do a spoke-to-spoke tunnel, we're going to have a registration request come into the hub, and the hub is going to reply back to the spoke with the remote spoke address. Okay, now on the spokes, if we take a look at our routing protocol information and we show IP route eigrp, we're learning about 150.1.2.2, which is the loopback interface of router 2, and 150.1.3.3, which is the loopback interface of router 3. Now, what's important about this particular output here is the next hop value. Okay, the next hop value was maintained as the original next hop of 155.1.0.2. The reason why is that in their example on the hub, when we show run interface tunnel 0, we have the command no IP next hop self eigrp1. Okay, normally the hub is going to be setting the next hop to itself, which would mean that anytime we want to go from router 1 over to router 2, we would go up to the hub first. But in this particular case, we're going directly over to the remote spoke, which is going to allow us for our spoke-to-spoke tunnels. Okay, to show this, we're going to do a trace route to 150.1.2.2 and source this from 150.1.1.1. We should see initially we go up to the hub in order to do the resolution request. And the next trace route that we send is going to go directly spoke to spoke. So if we go back to our packet capture and download the packet capture again, and we look for the NHRP messages, we see an NHRP resolution request. Okay, in the resolution request, in the mandatory part, it says router 1, who is 169.254.100.1 with the VPN address 155.1.0.1 is trying to reach 155.1.0.2. So we notice that router 5 then replies to router 2, saying that router 1 is trying to resolve you, And router 1 has the address of 169.254.100.1 mapping to 155.1.0.1. Okay, we then get a response that's going from router 2 back to router 1. And this is going to show the mapping between router 2's address 169.254.100.2 to 155.1.0.2. Okay, we could also see this if we debug INHRP on the command line. And let's look at the show IP route eigrp. Okay, we're going to trace route to 150.1.3.3, which is going over to router 3. Okay, over to one of the other DMVPN spokes. So we trace to 150.1.3.3, source of 150.1.1.1. And what we should now see is that we're adding the tunnel endpoint. The VPN address 155.1.0.3 maps to the outer address 169.254.100.3. So if we look at the show IP NHRP, we should have a dynamic mapping that we know to get to the remote spoke 155.1.0.3, we need to go to the NBMA address 169.254.100.3. So for subsequent trace routes, we're going to be going direct spoke to spoke as opposed to going up to the hub and then back down. But for the initial trace route, it goes up to the hub while we're doing the resolution. The hub redirects this back down to the spoke. The spoke then sends the resolution reply back to router 1. And then we know that there's a mapping between the VPN address and the NBMA address for that particular spoke. Okay, so this is what the network looks like when we're not running IPsec. So if we go back to our packet capture and we look at the ICMP messages, we would see the two headers, the inner header, the 155.1.0.5, and then the outer header, the 169.254.100.5. But when we're running IPsec and we do a packet capture, the only thing that we're going to see is going to be ESP, the encapsulated security payload, which is going to be the post-encrypted packet over the GRE tunnel. Okay, so let's go ahead and add the crypto configuration in. So the first thing that we have is going to be the crypto ISACAMP policy, which is made up of these attributes that we need to match in order to form the phase 1 policy, including the authenticator. Okay, so we have the password Cisco 47, 47 being the protocol number of GRE. And then we have the crypto transform set. So we're specifying that we're using ESP AES for the encryptor and ESP SHA HMAC for the authenticator. This is going to be for the phase 2 of IPsec, which is going to be the actual data plane tunnel. Okay, we then take the transform set and we call it from a crypto profile. Then the crypto profile is going to be applied under the tunnel interface with the tunnel protection command. Okay, so this is going to go on all of the DMVPN hub and spokes. Okay, so starting on the DMVPN hub, let's do show run section crypto. Okay, we already had a pre-shared key configured, which was just Cisco. So we need to make sure that that's matching on the DMVPN spokes as well. Okay, notice that the eigrp neighbors go down. This is because we're now expecting the packets coming in the GRE tunnel to be IPsec encrypted, which in this case, the DMVPN spokes don't yet have the IPsec configuration done. Okay, so let's do the same thing on router 1. We have the crypto ISACAMP policy. And we have the neighbor come back up. Okay, the eigrp neighbor come back up. Okay, so same thing is going to be true on router 2 and router 3, which are the other DMVPN spokes. Okay, from router 5, let's look at the show DMVPN. Okay, we have the registrations that are showing the mappings between the NVMe addresses and the VPN addresses. Next thing that we're going to look at is the show crypto ISACamp SA, which is going to be the phase 1 negotiation for the IPsec tunnel. So we should have a tunnel that goes between router 5 and router 1, router 2 and router 5, and router 5 and router 3. Okay, so the IPsec tunnels are going to be nailed up between the spokes and the hub. The spoke-to-spoke tunnels are going to be on demand based on our routing protocols, though. So based on how we send the traffic patterns, if we go spoke-to-spoke, then we're going to initiate a new IPsec tunnel. Okay, the second verification we would look at here is going to be the show crypto IPsec SA. So this shows the actual encapsulation and decapsulation of the IPsec packets. So we have a tunnel that's going to router 5, from router 5 to router 3, that's encrypting IP protocol number 47, which is the GRE tunnel. And then we should see both an inbound and an S-bound security, inbound and outbound security association. So we have an inbound ESP security association that says it's using transport mode for ESP AES and ESP SHA HMAC. Okay, we should then also have an outbound security association using the same transform set, so ESP AES, ESP SHA HMAC, and we're running in transport mode as opposed to tunnel mode. So this is one of the very few cases where you run IPsec in transport mode as opposed to tunnel mode. And the reason why is that we already have the GRE tunnel header that is used to hide the inner VPN addresses. So we don't need 3 IP headers, we only need 2 IP headers. The inner VPN address, which is the 155.1 address in our particular case, and then the outer address, which is going to be the 169.254 address. Okay, so let's go ahead and create a new packet capture. On router 5. Traffic capture. Okay, we're going to do the default options. And then let's go ahead and look at, from the DMVPN spokes, show crypto ISACamp SA. Okay, we have tunnels that are going to the remote spokes as well. This is because we were previously sending traffic between router 1 and router 2, and router 2, router 1 and router 2, and router 1 and router 3. And then the show crypto IPsec SA is going to show the packets that are going over the tunnel. Okay, so we have a tunnel that's going from router 1 to router 5. We have packets being encapsulated. We have packets being decapsulated. Okay, let's look at the show IP NHRP. We have a dynamic mapping that's going to router 2 and to router 3. So if we look at the show IP route EHRP, we're going to do a trace route up to the hub, 150.1.5.5. It goes directly to the hub. We're going to do a trace route to the remote spoke, 150.1.2.2, sourced from 150.1.1.1. And it's going to go directly spoke to spoke. So this is the reason we have an IPsec tunnel between router 1 and router 2, is that previously I had already done this trace route, and the tunnel is then established on demand based on those traffic patterns. Okay, if we look at router 2 and look at the show crypto ISACamp SA, we have the tunnel that goes from router 2 to router 5, so from the spoke to the hub. And then we have one spoke-to-spoke tunnel that's going between router 2 and router 1. But we haven't sent any traffic yet that goes between router 2 and router 3. So let's go ahead and look at the routing table. We show IP route EHRP. Okay, we have the entry for 150.1.3.3. We're going to do a trace route to 150.1.3.3. It first goes up to the hub. We send the NHRP resolution request. We get the reply back in. And then the next packet is going to go directly spoke to spoke. Okay, if we now look at the show crypto ISACamp SA, we should have a new tunnel that's going between router 2 and router 3 that was established on demand. So if we show crypto IPsec SA, we have this tunnel that goes between router 2 and router 3 directly, and it's bypassing the hub. So for example, if I were to ping 150.1.3.3, source of 150.1.2.2, and let's send 100 packets, when we show crypto IPsec SA, we see that 100 packets were encapsulated, 100 packets were decapsulated over the tunnel that goes directly between router 2 and router 3. Okay, now if we look at the packet capture, the difference is going to be we're going to only be able to see the encrypted packets. We're not going to be able to see the actual control plane messages for the NHRP anymore. So if we look for NHRP, we don't see any hits. If we look for ICMP, we don't see any hits. If we look for ESP, we see the encrypted packets that are going from 169.254.100.5 to 169.254.100.3. So these are going to be all of the trace routes, all of the pings that we were doing. And some of these are going to be directly spoke to spoke. Okay, so this is the reason why we wanted to look at the tunnel first without IPsec, is that when we're doing a packet capture and IPsec is involved, the only thing that you can see is the post-encrypted packet as opposed to the control plane that's actually running inside of the tunnel. Okay, so next thing I want to talk about is the DMVPN phases. And if we look at the routing table on the spokes, if we look at the show IP route eigrp, one of the potential disadvantages of the current design is that the spokes need to learn exact routes to each other in order to form the direct spoke-to-spoke tunnels. So this would be a scaling limitation depending on how many spokes that you have on the network. If you have hundreds of spokes, then you could have potentially hundreds or thousands of routes that the spokes would have to maintain. Okay, one of the solutions for this is that we could go to the DMVPN hub and we could do a summary address. So we're going to go to tunnel 0 and say IP summary address eigrp1, and we're going to summarize 2/0. Okay, so just a default route. Okay, if we go back to the DMVPN spokes and look at the show IP route eigrp, the only thing that we have is now the default route that's coming from the hub. So if we do a ping to 150.1.2.2, we still have reachability. And if we trace route to 150.1.2.2, we're going up to the hub and then we're going back down. Okay, so this is the potential disadvantage of what we call DMVPN phase 2, is that in phase 2, if we were to do summarization, notice that the next hop is now listed as the hub's interface 155.1.0.5, and we've now disallowed the direct spoke-to-spoke communication. We have to go up to the hub and then back down in order for the routing protocol information to be completed. Okay, so this is where DMVPN phase 3 comes in, and where routing with NHRP with the next hop resolution protocol is going to come in. So the configuration of this is going to be really straightforward. It's only one command on each of the routers. So on the DMVPN hub, we're going to go to the tunnel interface and say IP NHRP redirect. And on the DMVPN spokes, we're going to go to the tunnel interface and say IP NHRP shortcut. Okay, same thing on router 2, interface tunnel 0. IP NHRP shortcut. Same thing on router 3, interface tunnel 0, IP NHRP shortcut. Okay, if we go to router 1, we're going to debug NHRP, and we're going to do another trace route that goes 150.1.2.2, where we now have the resolution request for 155.1.0.2 that's mapping to 169.254.100.2. Now, if we look in the routing table, what should have occurred is that we now learn NHRP routes, which are denoted by the H status code, that are going to be overriding the default route. So this is going to be just based on the longest match routing principle, that we have this 150.1.2.2/32, and it says it goes to 155.1.0.2. So for example, if we show IP route for 150.1.3.3, subnet is not in the table. If we show IPsec for 150.1.3.3, it says our longest match is the default route. Okay, we then do a ping to 150.1.3.3, source of 150.1.1.1. We do a trace route to 151.3.3, source of 151.1.1. And now we're going again directly spoke to spoke. Okay, when we show IP route for 150.1.3.3, we now have a more specific route learned from NHRP, and the next hop is 155.1.0.3. So the point of this is that on demand, you learn the routes that you need for the spoke-to-spoke routing, but you don't necessarily need to learn the routes for every possible spoke. So only based on the traffic patterns that you're actually sending the traffic will you install the NHRP routes based on the hub's redirect. Okay, so the idea is that the hub says the packet came in the tunnel interface and it went back out the tunnel interface. So I'm going to send an NHRP redirect message that includes the routing information about the next hop that they're trying to reach. Okay, so for example, between router 2 and router 3, if we show IP route 150.1.3.3, subnet's not installed because we can't, or we have not yet sent any packets direct between router 1 and or router 2 and router 3. Okay, if we show crypto ISACamp SA, we do have the IPsec tunnel that was pre-established between them. So let's clear crypto ISACamp SA, or clear crypto ISACamp. Connection ID is 1006 and connection 1005. Okay, let's show crypto ISACamp SA. And we now have the tunnel deleted that's going over to router 3, from 3 to 2 and from 2 to 3. Okay, so again, we look at the show IP route for 150.1.3.3. Subnet's not installed in the table. Okay, we then do a trace route to 150.1.3.3, source of 150.1.2.2. We go up to the DMVPN hub and we get the NHRP redirect message. Next step is that we now have a direct spoke-to-spoke tunnel. Okay, if we show crypto ISACamp SA, we should now have a tunnel that goes between router 1 or router 2 and router 3. And if we look at the show IP route for 150.1.3.3, we now have the NHRP route that is overriding the less specific route of the summary route. Okay, so we're learning 150.1.3.3 directly via 155.1.0.3. So we're using the direct spoke-to-spoke tunnel to reach the loopback of router 3, as opposed to going up to the hub and then back down. Okay, last thing I wanted to touch on here is going to be when we're running dual hubs between are on the same DMVPN cloud, because the limitation of the current network is that if we were to lose the DMVPN hub, we can't send the registration or the resolution request up to the hub in order to form the direct spoke-to-spoke tunnels. Okay, so in this example, we're going to use router 5 as the hub primary, and we're going to use router 4 as the hub secondary. Okay, so the changes that we're going to make are going to be on router 5. If we look at the show run interface tunnel 0, we first need to do a mapping to the other DMVPN hub, which is going to be the IP NHRP map statement. Okay, we're mapping 155.1.0.4 to the NBMA address 169.254.100.4. Okay, we're also going to map multicast IP NHRP map multicast to 169.254.100.4. Okay, so if we go back to our DMVPN hub configuration, we're going to do the same thing, but this is going to be on router 4. And we're going to have these additional mappings for the primary hub. Okay, so we're going to map 155.1.0.5 is mapping to 169.254.100.5. And we're mapping multicast to 169.254.100.5. Okay, everything else is going to maintain the same, including the tunnel protection. Okay, so let's go ahead and apply this on router 4. And if we show IP EIGRP neighbors, we now have an adjacency over to router 5. Okay, from the DMVPN spokes, we're now going to have duplicate mappings that go to the secondary hub. So if we show run interface tunnel 0, we're going to have a mapping that goes to router 4, both for unicast and for multicast. And we're going to have a mapping to the next hop server going over to router 4. So on interface tunnel 0, we're going to say IP NHRP map 155.1.0.4 to 169.254.100.4. IP NHRP map multicast to 169.254.100.4. And the IP NHRP next hop server is also 155.1.0.4. Okay, and notice that we now have a new adjacency over to router 4. We're now going to be tracking both of the hubs from a routing protocol point of view. Okay, this is from the DMVPN spoke. Okay, same thing is going to be true on router 2. On interface tunnel 0, we're doing mappings over to router 4 statically. And we should see an EIGRP adjacency come up. Okay, same thing on router 3, interface tunnel 0. We're mapping router 4 both from a unicast and a multicast point of view, and we're specifying it as a secondary next hop server. Okay, next let's look at our routing. If we look at the show IP route EIGRP, we see that we're learning 150.1.2.2, and the next hop is 155.1.0.2. This is actually going to be coming from router 4. So if we show IP EIGRP topology for 150.1.2.2/32, it says this came from router 4. Okay, we're still running DMVPN phase 3, so we're doing the direct spoke-to-spoke tunnels regardless of what the routing table says. So let's go over to router 4, and we're going to also do a summary address, IP summary address EIGRP1 for all zeros. Okay, on router 1, we're going to show IP route EIGRP, and we see the summary address that's coming from the primary hub. Okay, if we debug NHRP, we're going to go to router 5 and we're going to shut down the tunnel interface. Router 1 should learn about this It says the next hop server 155.1.0.5 is down. And we're now polling 155.1.0.5. We're polling it every 4 seconds, then 8 seconds, then 16 seconds. We're trying to see, did the next hop server come back? And can we use this for resolution requests? Okay, if we do a trace route to 150.1.3.3, we're still using the direct spoke-to-spoke tunnel, even though the next hop server is down. Okay, so if we show IP route eigrp, we have this default route that's now coming from router 4 as the backup for router 5. Okay, so let's go ahead and shut the tunnel interfaces down. This is going to delete our mappings. Okay, and as someone mentioned here for DMVPN phase 3, I forgot to put the IP NHRP redirect message on or command on router 4 as well, which is going to be required for the DMVPN phase 3. Okay, so let's look at router 1 and look at the show IP NHRP. We have static mappings that are going to both of the hubs that are going to router 4 and router 5, but we don't have any dynamic mappings learned about the spokes. Okay, if we show IP route eigrp, we're learning a default route just from router 4. Let's go ahead and trace route to 150.1.2.2, source of 150.1.1.1. And notice in this case, we're now using router 4 as the next hop server, as the DMVPN hub. Then we go over to router 2. Okay, we get the resolution reply that router 2's mapping for 155.1.0.2 maps to its NBMA address 169.254.100.2. And our subsequent trace route now is going to go directly spoke to spoke. So if we look at the show crypto ISACamp SA, we should have a tunnel that's in the QM idle state between router 1 and router 2. And if we show crypto IPsec SA, we should have a tunnel that goes directly between router 1 and router 2. Okay, so if we ping to 150.1.2.2, source of 150.1.1.1, repeat count of 100 packets. Show crypto IPsec SA, we can see we had 100 packets encapsulated, 104 packets decapsulated, so we are using the direct spoke-to-spoke tunnel between router 1 and router 2. Okay, when router 5 comes back, we should be able to detect this on router 1. It's going to take a minute for it to pull that the next hop server is back up. Okay, next up, server 155.1.0.5 is up, and we have a new eigrp adjacency that's going over to router 5. Okay, there was a question here about the primary and the secondary hubs. It's going to be based on the eigrp metrics. So there's something different here in the default config here that we're not load balancing between router 4 and router 5 because router 4 has a worse metric to something. So it might be the delay, it might be the bandwidth. But if we look at the show IP eigrp topology for 0000/0, we should be learning the default route in multiple directions. Okay, so if we notice the metrics, we're learning 2816 in from router 5 with a delay, total delay of 50,010 microseconds. Then we're learning it in from router 4 with 128.256, a total delay of 55,000 microseconds. So the delay on router 4's interface must be higher for some reason in this default config versus router 5. But it doesn't really make a difference because we don't need to load balance between the two of them, because we're only using the hub in order to request the address of the spoke. Once the spoke address is resolved, we're going direct spoke to spoke, and the traffic is not going through the hub. So the hub is mainly used just in the control plane. It's not going to be used in the data plane. Okay, if we show IP route, we see the NHRP route that came in coming from 150.1.2.2. Okay, if we show IP route for 150.1.3.3, we don't currently have this installed in the table. So we're going to trace route to 150.1.3.3. We go to our primary hub, we go to router 5, and then we go back down to router 3. Okay, we're sending the resolution request on the tunnel. We're trying to resolve 150.1.3.3. We got this resolved to 155.1.0.3, which maps to 169.254.100.3. So if we show IP NHRP, we should now have a dynamic mapping for the loopback of router 3. It says to go directly to the spoke 169.254.100.3. So if we do the trace route again, we now go direct spoke to spoke. We're not going up to the hub. Okay, so there's not a need to load balance between the two hubs, because the only thing that we're using the hub for is just this first initial packet in order to get the resolution request. And then we're redirecting the packet back down. Then all the subsequent traffic is going to go direct spoke to spoke between the DMVPN spokes. Okay, so to recap our configuration, if we look at the show run interface tunnel 0, when we're dealing with dual hubs, we have multiple mappings. So we have a static mapping for unicast and multicast for the primary hub. We have a static unicast and multicast mapping for the secondary hub. Then we have the next hop server router 5. We have the next hop server router 4. Okay, from the DMVPN hub itself, show run interface tunnel 0. We have a static mapping that goes to the secondary hub, and we have the multicast mapping. Okay, this is what's going to allow them to form eigrp neighbor relationships, that we should see an IGP neighbor relationship between the two hubs over the DMVPN tunnel. Okay, then from the DMVPN spokes, we should see that we have eigrp neighbors to both of the hubs. Okay, so this is going to be the extent of what we're covering today with DMVPN. So in our All Access Pass library, there is a DMVPN deep dive series, as well as a DMVPN series under CCIE Enterprise Infrastructure that goes into more detail on phase 1, phase 2, phase 3, and then also on the use of the dual hubs for DMVPN. Okay, there's a question, is there any good place to check out dual DMVPN hub design and configuration? And let me see if this document still exists, which is it should just be the DMVPN design guide. Scalable DMVPN design and implementation guide. DMVPN design guide. So I'm not 100% sure why there's an error message on the documentation there, but there is a PDF on Cisco's website that is the DMVPN design guide. That's under the Cisco validated designs. It's under the the CVDs. So this is another good resource for more information on DMVPN. There's a question, is DMVPN Cisco proprietary? I believe their implementation is, but it's made up of open standards protocol. So NHRP itself is an open standard protocol, and everything else is open standard. So IPsec, BGP, NHRP, it's a combination of open standards protocols that are used to get to that effect for the DMVPN. There's a question, are all the tunnel interfaces on the spokes and the hub need to be in the same IP subnet? Yes, so in the inside of the tunnel, yes. In the outside of the tunnel, no. The only requirement for the underlay is that we have IP transport. So as long as you can ping between the hub and the spokes, that's going to be the only requirement in order to form the tunnel. Okay, there's a question, why transport mode and not tunnel mode? This is because we already have the GRE tunnel that's encapsulating the VPN traffic. So if we were to use tunnel mode, there would be 3 IP headers. There would be the 155.1.0.5 from the hub. There would be a 169.254, and then another 169.254 that would be the IPsec header. Okay, there's a question, can we disable split horizon only for the tunnel interface in eigrp protocol and not with the IP split horizon eigrp X command? So we're disabling it only on the tunnel interface by applying that command on the tunnel interface itself. So if we look at the hub and we look at the show run interface tunnel 0, this is applying just to the tunnel interface. It's not applying to any of the other Ethernet interfaces. If this was the named eigrp process, we would do it under the AF interface tunnel 0 and say no split horizon. Okay, there's a question, do we need the IP NHRP map command for DMVPN phase 1? Technically, no, because with phase 1, you're using point-to-point tunnels on the DMVPN spokes, and you're using a multi-point tunnel on the hub. The only thing that's really needed is the IP NHRP next hop server command on the DMVPN spokes for phase 1. But phase 1 is pretty much considered obsolete. Any design that you see today is generally going to be running DMVPN phase 2 or phase 3. Okay, there's a question whether the NHRP network ID has to be unique in the entire network or could it be common? It does need to match for an individual DMVPN network. So if you're running multiple tunnels, you would have multiple network IDs, so they would be unique on a per tunnel interface. But this does need to match between the devices that are in the same NHRP domain. Okay, there's a question, I get the error on router 5 after doing shut, no shut on the physical interface, receive packet, invalid SPI. This is because from the DMVPN spokes, the IPsec tunnel is still up. And when you shut the tunnel down, it deletes the negotiation on one side, but it doesn't delete the negotiation on the other side. So the simple fix for this is to shut down the tunnel on the hub and the spokes, and then no shut the tunnel on the hub, and then no shut the tunnel on the spokes. Okay, there's a question, once the spoke knows how to get to the other spoke directly, how long does the spoke retain that information? In other words, if the hub ever goes down, would the spoke continue to work for a while? Yes, it would. Okay, this is going to be based on the NHRP timeout. If we show IP NHRP, it expires in 1 hour and 51 minutes. So it looks like it's a 2-hour timer by default. You can change these timers with the hold time, the IP NHRP hold time, but by default, it's a pretty long timeout that it's going to hold the cached entry. Okay, there's a question for DMVPN phase 3. Do we need the underlay IP addresses to be reachable between the spokes? Yes, you do. So the underlay needs to be reachable through everything, because that's what's actually forwarding the packets when we look at the packet capture in the middle. The underlay in this case was the 169.254. So they were on the same segment, but in most typical designs, you would see that they're on a different segment and you're using a different underlay routing protocol in order to gain reachability towards the, between the hubs and the spokes. Okay, there's a question, can you turn off spoke-to-spoke communication? We would like to keep all remote sites segment in our installation. Yes, if you run DMVPN phase 1. So in DMVPN phase 1, you use point-to-point GRB tunnels on the spokes, and you use a multi-point tunnel on the hub. And then there's no direct spoke-to-spoke traffic. All the tunnel traffic would go from the spokes to the hub. Okay, there's a question in phase 3 setup for the hub. I only had IP NHRP redirect on the hub and IP NHRP shortcut on the spokes. Correct. So on the spokes, if we show run interface tunnel 0, we have the IP NHRP shortcut command. And on the hub, we have the IP NHRP redirect command. There's a question, how do the spokes choose the primary hub? Is it an order of operations? I believe it's just based on the config order that router 5 is listed before router 3 in the configuration. So if you were to delete these two statements and then swap them, then it would prefer to use router 4 over router 5. Okay, there's a question with primary, secondary hubs. Would you load balance or would you simply ensure redundancy? You would just be ensuring redundancy. There's a question, what would be the behavior in tunnel mode for IPsec? It would just be additional overhead in the encapsulation. So the packet would be bigger and it would take a little bit longer to encapsulate it. So it's basically just an overhead type issue that transport mode is more efficient than tunnel mode in this particular design. There's a question, can multicast traffic originate from a spoke? You can do multicast between the hub and spokes, but you can't do multicast spoke to spoke unless you have a static multicast mapping between the two spokes, which is the workaround for doing multicast data plane between the spokes. So you can have multiples of these multicast mappings, which is what we have here. And if we look at the show IP eigrp neighbors, we have multicast reachability both to router 4 and router 5. So the spokes could exchange routes directly if you do mapping multicast statically. Okay, there's a question, will this be a single DMVPN cloud or multi-DMVPN cloud? This is considered single DMVPN dual hub. So single cloud, dual hub. Multi-cloud would just be multiple tunnel interfaces with multiple unrelated hubs. Okay, so we have time for about one more question here. Can static routes work in the underlay for DMVPN? Yes, you can. So you can use whatever routing protocol that you want for both the underlay and the overlay. But in the underlay, yes, you can use static routing. Okay, so I appreciate everybody coming out to class today. I hope you enjoyed our brief session on DMVPN. So there's definitely more detail in our All Access Pass library under the DMVPN class, and then also the DMVPN deep dive. We go through troubleshooting scenarios. So what are the common problems that we run into with DMVPN, and what are the workarounds that we can implement in order to fix the problems? And like Brittany said, this session is recorded, so there is going to be a follow-up with more information about the recording. So thanks everybody for attending. Good luck in your continued preparation, and I hope to see you back here for further webinars at INE.